So the fish farm optimization algorithm follows or mimics the way a school of fish searches for its food or prey. And this algorithm has mainly 4 steps. So let us discuss this with an example. The example is that y is equal to x square is the objective equation. Now x is your design variable which can take any value in between 0 to 1. X can be fraction but it must be a real number. So this is another constraint. So you have to put the values of x to change the values of y, and your goal is to maximize y. Okay, so the more the values of y, better is the optimization. Thank you. So this is the example optimization problem. So the first step will be to generate random values of x. So for any meta-heuristic algorithm, this is the first step. They randomly generate values of x of the independent functions. So here also you have to randomly generate the values of x within this domain 0 to 1. So that value can be fraction, but it must be a real number. So satisfying these two constraints, you have to generate random values of x. So here I is the number of population. Now it will depend upon you, the user. So for demonstration purpose, I am saying that I is 4. So 4 different values of x will be randomly generated from the 0 to 1, the domain or such domain of x. And x is your design variables, and y is your objective variable, and y is equal to x square is your objective equation. So for the random values of x, you will get, you have generated 4 values of x randomly. So 4 values of y will also be, you will also get 4 values of y, because ultimately you have to optimize this. Y is equal to x square. So you will have 4 different values of y. So here I is denoting the number of population. So y1 means y I is equal to 1. y2 means y I is equal to 2, and so on. And t is generating the iteration, number of iteration. T is the current iteration, t plus 1 is the new iteration. Now what happens is, if I will say that, and what is the next step? Now you have 4 values of y, and the more the values of y, better is the objective function. That means if y1 is greater than y2 is greater than y3 greater than y4, then y1 is the fittest one. So our next step will be to generate new values of x. Now we have a set of 4 values of x that we have generated randomly at the first step, and got 4 values of y. Now in the second step, we will not generate the values of x randomly, but we will generate the values of x following a system or rule. Now this rule is given by this equation, x I t plus 1. As I have already said, I is the number of population. So simultaneously we will generate 4 new values of x. So as I is equal to 4. Now this is t plus 1 means new iteration, t means current iteration. They also say it at new position. If it is t plus 1 in the superscript, they say it as new position. And if it is only t, then it is old position or current position, whatever you may which you can refer it. And RAND is the eternal random function for generating random values in between 0 to 1, and of course they will be fraction. And multiplied by this weight parameter, which is again given by this equation. So what is the equation? This is also W at population I, t plus 1. This means this is the new W. This is the old W or current W. And W is the weighted parameter or weightage. And this is actually del F, matlab the old weightage plus del F divided by max of all del F. Now you will say, what is del F? Very easy. Del F I, there will be a I, because for each I there will be one del F. Because we have 4 Y's, 4 population, I is equal to 4, so we will have 4 del F's. So what is this del F is? Del F is actually Y I t plus 1 minus y t I. So the value of objective function at t plus 1 minus the value of objective function at t for the ith population, this difference is given by del Fi. And as you can recall, there are 4 i's, so there will be 4 such differences, correct? So there will be del F1, there will be del F2, there will be del F3, del F4. And as this is a maximization function, the maximum del F indicates the maximum improvement of the objective function. So that maximum del F among all the 4 del F's will be written here in the denominator. And the above one is the del F at I. So numerator is del F and denominator is maximum of all del F. It will be added with the old weightage to get the new weightage. So the thing is this is the way we, and you know this weightage will be, substitute this one, and it will be multiplied by random function, and it will be added to the old position or old value of x to get the new value of x, and for each population there will be one new x. So this is the case. But what happens when there can be 2 cases? One case will be del F can be equals to 0, del F can be not equals to 0. So if del F is equals to 0, that indicates that there is no improvement happening in the objective function. So what happens is, or what is the solution for that? This indicates a local minima, and the solution is to contract the search domain. Contract search domain. Okay, so contracting the search domain. That is, search domain means in our case it is 0 to 1. For different cases, different search domain is there. For search domain indicates the domain from which feasible solution of x is retrieved. So these things we have already covered. So if del F is equals to 0, that means there is no improvement. And so what will happen is we have to contract the search domain. And what will I was just telling I was incorrect. When del F is equals to 0, it is showing that no improvement is occurring. Then we have to expand the search domain to include new values of x's. Correct? So how to get these new values? This can be indicated by this one. Where it is? You see, this is the pseudocode. If weight is increasing, weight means optimal values of y. Actually, what happens when the school of fish is searching for its prey and it ultimately gets it, it will consume the prey and automatically its weight will get increased. So increase in weights signals that there is the prey. In that location prey is there. So those fishes has already got the solution. So what happens is all the other fishes of the school of fish follows that fish. So similarly what we mimic is if weight is increasing, then del f is not equals to 0. Okay, so what we do is when weight is increasing, that means we have already got the optimal solution. So now what we do is that we want to select only the specific values of x for which the value of y will be maximum, not any other non-dominant value of x. Dominant value of x means only those values of x we want to concentrate, or we want to narrow down our search for which y is the maximum of all the x for all cases. Okay, so to do that we have to contract the domain. We know that let us give another example. If in this part we are getting the better values of x for which y is increasing like anything. So if I slowly contract this domain from this to this to this, so what is happening? We are concentrating on those most optimal values of x for which y is maximum. We are concentrating on those x's only, neglecting the semi-optimal solution. So that is why what happens when the del f is increasing or the weight is increasing, we decrease the search domain. Now, if weight is increasing, then we decrease the search domain. Else, if there is no increase or decrease of weight, what happens is we increase the radius of search to include new values of x, such that to look after that where is that optimal value of x for which del f will begin to change. So if weight increasing, then contract the radius of search to concentrate only on the selective optimal values of x. If not, you increase the domain, the area of the domain, to include more new values of x. So for the first case, what happened? We try to calculate a weighted average W. Okay, and so this W is actually summation of all the x's generated, xi, summation of the product of xi multiplied by weight of that x's. So that is actually, W is actually xi's, here we have generated only 4 values of x, so 4 values of x, so x1 will be multiplied with the weight of x1 plus x2 into w2 plus x3 into w3 plus x4 into w4. This will be in the numerator, and in case of denominator, just the summation of all the weights. Now you will say, from where we are getting these weights? Yes, there is the weights. This is the equation of weight. W, old W plus del f divided by maximum of del f. Okay, so once you get the weighted average, uh, this is indicated by P, a term B. Now you put it, what happens is this B term will indicate your contracted search domain. But if you want to increase the search domain, then the same B term can be used in this equation, this new equation, where the new values of x will be calculated like this is the new value of x, this is the old value of x, minus this is the weightage, right? This is S IND, this is the weight value or weight parameter. Same as this one, same as this one. Okay. Now what happens is in this case, in the initial case, what happens? To find the new position of x, we are adding random value multiplied by the weighted parameter to the existing value of x. But in this case, when we want to increase the search domain, what we do is we are adding the random value and the weight parameter, the product of random value and the weight parameter, and the subtraction of this b value from the current value of x. That means x minus b divided by the distance between the x and b. Okay, so this thing will be also multiplied with the random function and the weight value and then added to the old value of x. So this thing is actually x minus b, the difference of x and this b divided by the distance between x and b. Okay, and this is the case. So what happens when weight is increasing? So weight is increasing is acceptable for the maximization problem. For minimization problem, weight decreasing will happen. So at that time we have to contract the search domain. So we are using just this weighted, the value of b as the weighted average of x, all the x's. All the x's means the values of x's at the same iteration but for different population. But for when we want to increase the search domain, what we are doing, we are calculating the new position by adding to the old position the product of weight parameter, random function, and the difference between x and b in the numerator divided by the distance between x and b in the denominator. But this very large, this one will be used only if del f is not changing. That means the optimization function or process has fallen or has felt into the local minimum. Only then, that means if there is no improvement of objective function, del f is equals to 0, then only this equation will be used. Otherwise, you will use this one, this b, to contract the search domain, or there is another equation also to direct the school of solution. If del if not equals to 0, you can also use the I function, identification function, to the existing equation of finding new values of x. So this is one new thing. You see, this is x t plus 1, new values of x. How it is found? The old value of x plus I. And I is nothing but your weighted value of the difference between the objective function in between two iteration. Here it is, above is x into del f divided by summation of all del f. So same thing like this, but instead of weight, here del f is there. Only if you replace W from this equation and use the term del f, the difference between the value of objective function in between two iterations, then you will get the function I. And when you add I to your old x, you will get new x. When you will do it? When del f is not equal to 0. So if del f is equal to 0, then you straight away, del f is equal to 0, then you straight away use this function. So let me summarize as a whole what will happen in case of fish swarm optimization algorithm. First step is generate random values of x within the feasible domain. So let it be 4 values for us. So I will become 4. And before the beginning of the algorithm, you need to define how many population you want to generate for your design variable, and also the number of iteration. These two are most important. So let me come back to this. Say we will iterate this. T is the number of iteration. Iterate 2000 times, and we will generate 4 number of populations. So I is equals to 4. So what we will do? So after generating the random value of x within the feasible domain of 0 to 1, we put these values of x into the objective function. Correct or not? So we will get 4 different values of y. So more the value of y, as this is a maximized function, more the value of y, better is the solution, fitter is the solution. Okay. So after then, what will happen? So after then, what will happen? This objective is maximization. So higher the value of y, better is the result, fitter is the result. Now after doing randomly generating the values of x, we will now generate the new values of x as per the fish swarm optimization algorithm. It is also in short written as fish swarm optimization algorithm, FSOA. So the new value of x is generated like this. The old value of x is x ti. T is your number of iteration. I is the number of population. So for 4 population, 4 new values of x will be generated with the help of 4 old values of x. So how it will be generated? This is the random function. Random function means, as you know, random number generated. Any number within 0 to 1 will be generated. It will be a function, but it will be random. And this random number will change for each iteration. Okay. Now this random number is multiplied with the weight parameter, SIND. Okay. Now what is this weight parameter? Weight parameter is this. This new value of weight is generated with the help of, again, old weight value plus del f divided by maximum of del f. This del f is the difference of objective function in between two iterations, not in between two populations. Mind it, in between two iterations, I. So this del f, I have already shown, this del f I is actually the difference between yi at t plus 1 minus yi at t. So these are the iteration. This is the old iteration, this is the new iteration. This is y is your objective function generated for the value of x at I population. So yi superscript t plus 1 minus yi superscript t is your del f I. Many people confused it with population. This is not the population. Difference of objective function for population. This is difference of objective function in between two iterations. And then this del f is compared for each of the population, because for del f I, 1, for I is equal to 1 there will be one del f, for I is equal to 2 there will be another del f, for I is equal to 3 there will be another del f, for I is equal to 4 there will be another del f. So in total there will be 4 del f's. So among these 4 del f, the maximum value of the del f, as this is a maximization problem, you will identify the maximum value of the del f and put it into this denominator. So del f by maximum of del f added to old value of weightage will give you new value of weightage. Now put this new value of weightage here as a weight parameter, multiply with the random number, add it to the old value of x, generate the new value of x for each iteration, sorry, for each population. Okay. Now what happens is there can be two cases. One is del f not equals to 0. That means the optimization is increasing. Okay, objective function is increasing and our goal is maximization. So more the increasing optimization, better is it. So del f not equals to 0 is very good thing. So what will happen is, if there is a del f not equals to 0, you can generate the new value of x with the help of an I operator. This I operator is nothing but identification operator, which will actually guide the other value of the population towards the optimality. Because in case of real value of in reality, when a school of fish means a population of fish is looking for a prey or food. So some population, some of the fishes may get the prey or may get the food first compared to the other member of the population. But the other member of the population can detect it by observing the difference in weight of that fish. If they detect that the weight of the fish is increasing, then they understood that yes, this fish has got the food or prey and he have consumed it, so that's why his weight has increased. So at that moment, the other member of the school, as you know, a large gathering of or a pack of fish is referred to as a school. So that other member of the school also follows that fish. So that is why this I is that identification operator. So now instead of multiplying random number with this weight parameter, you can straight away add this I operator with the old x. With the old x, add I operator. What is I? I is the summation of the product value of the del x multiplied by del f. Del f I have already discussed. Now del x is the difference of the values of x in between two iterations. Okay, so del f means the difference of values of y in between two iterations. And you add for each of the population, there will be one del x, one del f certainly. So multiply that del x del f and add it. So that will be your numerator. And in the denominator, what will happen? Just add all the del f's of each of the population. Del f we all know. So for each y or objective variable, we'll get one del f. So, or to be more precise, for 4 number of x, we'll get 4 number of y, and also we'll get 4 number of del f certainly. So add those del f's and place it into the denominator. So in the numerator, add the difference of x multiplied by the difference of y in between two iterations for each of the population, divided by difference of y in between two iterations for each of the population. Simply add it. This ratio will be your I operator. Add this I operator to the old x to get the new x. If del f is not equals to 0, that means objective function is increasing. We are getting fitter solutions. But when del f is equal to 0, that means the objective function is not increasing, neither increasing nor decreasing, so it has fallen into the local minima. Then you will use this equation. Then you will use this equation to get the value of nu x. So this equation is also similar to the earlier equations. Only thing is that you will add, yes, here also multiply random number with the weight parameter, and another term you will multiply, that is the difference between x, that is the value of design variable, and b divided by the distance between x and b. Now you will say, what is b? B is nothing but the weighted average of the weighted average of the what I can say, weighted average of the value of the input parameter or the design variables. So if you just observe this equation, this is, say, this I equation. I is equals to summation of the product value of difference of x multiplied by difference of objective function y in between two iterations for each population. Here, instead of del f, you use the term w. This is the term w. Okay, then you will get b. Okay, so this same equation is used to identify the decreasing domain when del f is constantly increasing, and we want to select or identify only the most optimal values of x, for which we are getting the most optimal value of y. So for that reason, we have to constrict the search domain. At that time, the equation we use is b equals to summation of the x's, that means the design variables for each population, multiplied by the corresponding weightage w. You add it, place it into the numerator, x into w, xi into wi, plus summation of xi into wi, I is equals to 1 to I, divided by all the summation of all the w of each of the population. That means wi summation I to I, sorry, I is equal to 1 to I. So this is the thing. So when you change this del x to x and del f to this w, we get the value of b. And when you use the value of b here as x minus b divided by distance between x and b, and multiply with the random number and this weight parameter s volume, then add it to the old value of x, we get the new value of x. When del f is equals to 0, that means it is neither improving neither decreasing in the local minimum. Then you have to increase the search domain. So to increase the search domain, you are using this equation. When it is the solution is good, solution is going on at the optimal direction, use this equation to get the new position of x. And for any other case, general cases, use this equation to generate the new values of x. But in the first iteration of the 0th iteration of the initial iteration, just randomly generate random values of x within the domain or constraint 0 to 1. So here only one variable is there, 0 to 1, but this algorithm can be used for multi-variable and also for multi-objective optimization. So with this, I finish. Thank you for your patience here.